to video this? Video it now?
Yeah, I'm videoing.
You're videoing me?
Yeah.
Oh god. Right, so, because it'll run out in a minute. Are you ready? So we're going to put some of the iodide ions in there. And, woo! You can see there that it's lowered the activation energy quite drastically, and it was meant to go in there. In the video you saw the catalysed reaction between hydrogen peroxide molecules breaking down to form water and oxygen gas. Now there's absolutely no way that hydrogen peroxide will break down spontaneously to form that much oxygen and water under normal conditions. So you saw that I threw in a catalyst being iodide ions. So the reason why this could never happen in the way it did is because of the activation enthalpy. It was far too high. So there's our reactants, hydrogen peroxide. We're expecting 2 molecules of those to collide together to release lots of energy, water and oxygen. Activation energy is huge. So what we needed to do is to put in a catalyst, and as you know, a catalyst provides an alternative route which lowers the activation enthalpy. So that took place in 2 steps. One of the hydrogen peroxide molecules reacts with an iodide ion, which then produces water, and what is called an intermediate, well, that must react with one of the oxygens to produce IO minus. Now this intermediate, we'll call that our intermediate, does not appear in the overall equation, so it must get consumed in the next step. So this has to get used up in the next step, our intermediate, which was IO minus, and guess what? We've still not used up 2 molecules of peroxide, so another molecule of hydrogen peroxide now must react with the intermediate to make more water and oxygen gas, and the iodide ion is regenerated. This is the intermediate, and in the second step the intermediate got consumed. If we add the 2 equations together, 2 moles of hydrogen peroxide, we can cancel out this intermediate because it appears on that side and that side. We can cancel out the iodide ions because they also appear on the other side, and therefore it looks as if our hydrogen peroxide has decomposed spontaneously on its own to form water and oxygen gas. The iodide ions are behaving as a catalyst because they appear in the first step and the second step, but it gets regenerated. It's not chemically changed. So we said a catalyst reduces the activation energy. So if we now draw our enthalpy profile again, this time with the catalyst, the hydrogen peroxide reacts with the iodide ions, but only one of them, to produce our intermediate, which was H2O and IO minus, and one of the peroxides still remains unchanged. This then reacts with the IO minus to produce our H2O plus oxygen and regenerates our iodide ions. So you can see that the activation enthalpy has been lowered, and it takes place in 2 steps. The rate equation therefore is dependent on the concentration of iodide ions, because without the iodide ions, no matter how concentrated our peroxide was, it didn't matter. Obviously we're relying on that colliding with that, so the rate equation for the first step is equal to the rate constant times by the concentration of the 2 reactants that are in the slowest step or the first step of the reaction. There's our rate equation. There is 1 iodide ion, so the rate equation contains 1 iodide ion to the power 1, 1 peroxide molecule 1. We say that the molecularity